you're all black right now. Stand by.
Yeah, I'll try turning my video off and then back on again.
All right.
And the video is starting up.
All right, stand by. We're looking for you. There we go.
My video is still starting up, I think.
All right. Let's see what happens here.
How's that?
Now you're just frozen, but we can see an image of you. Oh, and this is interesting too. We're going to have captioning on our end, Rungshin. If you're here for computer science,
so now you can see me, is that correct?
You're frozen on our screen. We're trying to figure out why. We're thinking Zoom does not handle 999 people connecting all at once very well. So stand by. We're going to keep tinkering here.
Well, that's better than a black screen.
OK, you're back. Oh, can you move your hand or something, Carter? Can you wave, Carter? Can he not hear me now? Carter, wave your hand. I mean, it can't be that delayed. Carter, he can't hear me. It's that much of a delay? Oh, my God. Carter, can you say something? I was about to say, if you're here for some computer science, technically this is computer science. It's just not working right now. But if you're curious, we're supposed to be seeing our colleague Carter, who's across campus, right there on the screen. Here's a little Zoomception. You might see yourselves now on Zoom. If you'd like to wave using a physical hand, if you're among the first 25 or so people on the screen here, you'll see yourself on the internet. Very meta. There we go. Rex, we see you waving, and Paul and Itza. I think we saw Paulo, Mohammed, Aziza, Aditya. Nice. So ironically, all of your cameras are working fine, but we are having some trouble here. Nice. Jermaine, Magdalena, Arthur and Sophia. Hello. Burkay. I guess we could just do this for a while. We could go through all the names. Ashika, hello. Kashal. Alessandro. Wow. All right, Rungshin's back. Yeah, I mean, if we lose Carter occasionally, that's OK. We should just try to get him back. OK. And what happens if we lose these monitors? Do I keep going? But it's not going to Zoom, probably. Because is my video stream going through this Zoom session or a different Zoom session elsewhere? So I should stop if this breaks. OK. All right. Well, why don't we just test the audio on both directions here? We've not done this before here. Let's see if anyone would like to say a hello. Baber, am I saying that right? Let's see if we can, Rungshin, unmute Baber, B-A-B-E-R, and see if we can't pin him on the screen to say hello. Give us a moment just to figure out how to use Zoom with 1,000 people here. One moment. Baber, B-A-B-E-R, if I'm saying it right, if you're able to search. In the future, I'll just be able to tap an icon, but this is not CNN, so we can't do that yet. OK, there we go. Baber, you're on the internet. Do you want to say hello to the world?
Hi, Professor. How are you?
Good, thank you. How are you?
I'm fantastic. I'm so excited to be here. I've been going through the edX version, and I'm a professor here in Istanbul, by the way. I teach mathematics, but I love your class so much, and I'm so excited to be here for the dress rehearsal. Thank you very much for having us all.
Oh, well, thank you. And this is wonderful too, because if we can't get Carter back in Cambridge here, we might need you to lend a hand from Istanbul, from afar. All right,
absolutely, my pleasure.
Nice to meet. Let's see. Do you want to go back to gallery mode, Rungshin? And how about just one other hello before we dive into today's class? Malak, if I'm saying that right, M-A-L-A-K. Can we try to pin Malak if you're comfortable saying hello too? Give us a moment to find you. Okay, Malak, am I saying that right?
Yeah, I'm so glad that I'm here with you today in person, and I'm so excited because I was always so passionate about computer science and programming. So I'm very glad I'm here with you today.
Well, likewise. Nice to meet you, too. And I hope you won't mind. We don't really have time to do 997 other introductions, but looking forward to seeing everyone online in CS50's communities. I'm going to keep my mask on today, given the circumstances in the world. I will do my best to make bigger, grander gestures so you know when I'm happy or sad, even though you can't see my face. But we'll also try to work through any technical difficulties along the way. Let me put up CS50 back on the screen here. And let me check with the team if we are ready to go. All right. Well, thank you. You can't see them all. I'm the only one on stage, but we have this amazing team of talent behind the cameras, the audio, the lights, the action, everything. So my thanks to them. And do just stop me if anything breaks. All right. Sure. Did we get Carter back yet, Rongchen? Okay. Okay. All right, this is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. And this is a class that I myself took some 25 years ago today. But it wasn't necessarily going to be the case. In fact, when I was a sophomore here at Harvard years ago, I rather didn't get up the nerve to take even this class until I could just sit in on it for just one day first. And it was only when the professor, someone by the name of Brian Kernahan at the time, allowed me to take the class pass-fail, that I was able to get over my initial fear factor of failing or just not doing nearly as well in this kind of class as I might have in courses that were much more familiar. In fact, I even have my binder of CS50 materials from the fall of 1996, and I took a photo of it literally last night. This is the very first program I myself wrote in a language called C that you yourselves will know in just a few days' time. And while it might look a little bit cryptic, indeed, all this program does is say on the screen, by printing to it, hello, CS50. And now if it's any reassurance, especially if you're feeling yourself among those less comfortable, you're not really sure if you can or should be in a computer science, let alone programming class in the first place, perhaps take some comfort in the fact that even I lost 2 points on my very first program, but nonetheless made it to the finish line ultimately. What ultimately matters in this course, though, is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. Indeed, the only experience that matters over the next several weeks, the next several months, is how well you do versus where you feel you are at today. It's not a competition, but rather an opportunity, we hope, to push yourself beyond your comfort zone, learn a new skill, be able to create more artistically, more technologically, whatever thoughts and ideas you might have in your head, and ultimately bring them to life on a computer. In fact, if you are indeed feeling yourself among those less comfortable, know that 2/3 of CS50 students, both here and beyond, typically have never taken a computer science course before. So even though it might sometimes feel otherwise with someone's hand always going up in the air or someone else answering very confidently some question that I or one of the teaching fellows might ask, realize that odds are someone to the right of you, someone to the left of you is just as uncomfortable and inexperienced as you yourself are. But what is it you can do? Well, one of my favorite games as a kid was this one here, Super Mario Brothers on the original Nintendo, so years and years ago. And if you consider, for instance, how you might bring something like this to life, be it on an old school game console, a Mac, a PC, a phone, well, let's try to distill what's actually in this image. For instance, let me go ahead and eliminate some of the distractions, and let's just focus on one of these pyramids, so to speak. And if you're unfamiliar with any of the Mario games, there's a character named Mario that runs, and jumps up and down, ultimately trying to get over barriers like this. Well, I don't quite know yet, certainly on the first 10 minutes of class, how I can implement graphics yet, so let's make it simple. Let's just do something I could type on my keyboard, like a hash symbol like this, to mimic the idea of actually creating these bricks. So how might I go about writing a program now that prints this kind of pyramid? Well, let me go ahead and toggle over to another computer here on which I've pre-installed some software for demonstration's sake. And I'm going to go ahead and create a file called mario.c. More on this in just a week's time. But C is a popular traditional programming language that you can create by just using your keyboard. And this is going to look very cryptic at first. But I'm going to go ahead and say include standard.io.h int main void. Inside of this curly brace, I'm then going to say printf, quote unquote, hello, how about hello, comma, CS50, just like I did some 20 years ago, and then go ahead and close that curly brace for symmetry's sake. And what I've just realized, actually, stupidly, thankfully this is a dress rehearsal, is I just wrote the wrong program. So we're going to back up and actually implement Mario and not actually do hello world. But that's why we're practicing here today live on the internet. So how do I go about printing a pyramid quite like this one here? Well, let's look first for the pattern. There's first one hash symbol, then 2, then 3, then 4. And if you think of this pyramid as having like a height of 4, 1, 2, 3, 4, it looks like on every level of this pyramid, I want to print out exactly that many hashes or bricks. So it turns out in C, you can express yourself from top to bottom iteratively, kind of in a loop or a cycle like this. For int, I gets 1, I less than 5, I plus plus. And then below this, I'm going to use a couple of more of these curly symbols. And then inside of this, I'm going to go ahead and simply do the following. For int j gets 0. Let's see. What did I want to do here? This is why we're practicing. There we go. I'm going to go ahead and say int j equals 0. J is less than I, j plus plus. And then inside of the curly braces, I'm going to go ahead and on every level of this pyramid, I'm going to use a command called printf. I'm going to print out a single hash symbol. And then at the very bottom of this program, I'm going to print out one cryptic-looking character for now, a so-called new line character. And what I'm now going to do is save my file and run a command, make Mario. And thereafter, I have made myself a program called Mario that on a typical Mac or PC, I would just double-click the icon and voila, it would pop up. But here, I'm going to use my keyboard alone and run Mario. And thankfully, I actually wrote the right program this time. But C, a language in which we'll spend the next several weeks, isn't necessarily the easiest language to use. It's indeed an older language, but newer languages have made this kind of programming even easier. For instance, let me go ahead and pull up another file, this one called mario.py. And this time use a language called Python that's a little more modern and a little more user-friendly. And I'm going to say something more succinctly like this. For I in the range of 1 through 5, go ahead and print out a hash symbol again times the total number that we're on. Now let me go ahead and run Python of mario.py, and voila, it's the exact same pyramid. But instead of typing out symbol after symbol, line after line, I did the same in just 2 lines. And this is all toward an end of better design. Indeed, among our goals in this course is not to teach you one language or another, but to teach you ultimately how to program and how to have different tools with which to solve those problems. Oh, the whole time? Wait, I thought you had the ability back there. Do we not? Not yet. OK. So apparently you might not. Did they see? Oh, I was green screened against the blue too. So what you really just missed was a really interesting exploration of 2 programs written in a language called C, followed by one called Python. Stay tuned for tomorrow when you can actually see them for real. All right. So now we're projecting properly. All good? All good? OK, and give me 1 second here. Okay, wardrobe change. All right. Okay, ready when you are? All right. All right, so we may very well have made a program using a couple of languages now, but let's do something more interesting than text. Well, with the right background and with the right tools, can you even bring your computer more audibly to life? Let me go ahead and now do this. Let me create a program called speak.py and see if I can't make my very own computer here actually speak to me thanks to some code. This time I'm going to use a symbol called import pi TTSX3, which means give me access to text to speech. Then go ahead and give me something called an engine. And that engine is going to be the result of using pi TTSX3.init. And what I'm going to do here now is have this so-called engine say, quote unquote, hello, comma, world. In which case, then I should, OK, got it. Note to self. And then the engine lastly is going to run and wait. Is that for me? No? All right, so let's see if these 4 lines of code now bring to life this program in a different way. Let me go ahead and run Python of speak.py, and let's listen.
Hello, world.
All right, perhaps not the most human-like voice, but indeed one that was synthesized from my own code. And you know what? Let me go ahead and go back into this program now. And let me go ahead and first maybe ask the human, the user, myself in this case, for their name. Let me write the command input, what's your name, question mark. And now let me go ahead and say not hello, but hello name, and use some special syntax here that's going to plug in that value. Let me go ahead and run now Python of speak.py. I'm asked for my name, and I'll type David. And let's listen.
Hello, David.
All right, so now the program's even more dynamic, and this was what, 5 lines of code. Let me add just a few final lines of code, all of which will make sense in just a few weeks' time when you yourself will be able to do this. Not necessarily from memory, and indeed, I have printouts of exactly what it is I want to type here. But let's do one last version here where I introduce the following. I'm also going to give myself access to speech recognition technology, and now I'm going to go ahead and simply print to the user, what's your name, much like before. And then after that, I'm going to have a few new lines of text. I'm going to say recognizer equals speech underscore recognition dot recognizer. I'm finding this is harder to type as I say it. With speech recognition dot microphone as a source that I want to listen to. Let me go ahead and get some audio from this recognizer now and listen to that source, all toward an end of getting a name from this so-called recognizer that's going to recognize for me, using Google's speech recognition software, that particular audio. And then lastly, and I'm thinking I'm going to make this in advance tomorrow rather than doing this live, which is getting a little tedious and cryptic, let me go ahead now and still synthesize the voice, and let's see if I did this right. Crossing my fingers for Python of speak.py. David. David? Well, that's why we're testing. All right, let's test this once more. Checking recognizer, speech recognition.recognizer with speech recognition.microphone as source, audio, recognizer.listen of source, name equals recognizer, recognize Google audio, init, say name. All right, this program is theoretically correct. Let's try it once more. David. Well, I don't think we'll be seeing this program tomorrow. David. Carter? Anyone? All right. Well, the students tomorrow will not see that particular program until we get it working. All right. So before we forge ahead now, I think we're going to nix some of that stuff tomorrow to speed things up. What is it that I did in each and every one of these examples? Well, I provided input to my program, as by typing it out and then inputting something like my name. I then received output, seeing, for instance, the bricks on the screen or the hello, David on the screen as well, or audibly pronounced. And this ultimately is what every computer program is ultimately about, taking input and producing output. And frankly, this is not specific to computer science or programming. This is life in general, taking as input some problem and producing as output some solution. And as such, among the goals in a course like this is not just to introduce you to tenets of computer science or programming specifically, but problem solving more generally. So what kinds of problems might we solve? Well, to solve any problems, we need to first all decide on how we're going to represent those inputs. We all need to speak some common language of sorts, be it English or something else. So in computer science, we might first consider how we're going to represent information, be that information a number, a letter, a word, an image, a video, a sound, anything else. Well, let me propose that in the simplest case, we can use our own hands to represent information. If I start taking attendance here, there's not many people today, but if I look at the Zoom tiles, I see 1, 2, 3, 4, 5. Unfortunately, on a single hand, I would seem to only be able to count in what's called unary notation up to 5. And so that's perhaps a bit limited. And frankly, you and I typically use not just our hands after a certain age, but a more general decimal system, where you don't just have single digits, literally and figuratively. You instead have numbers like 0 through 9, otherwise known as base 10. So you and I, when we express numbers, when not using our hands, we actually write them out using symbols like this. But it turns out computers are much simpler than you and I as humans. In fact, computers, even though they can seemingly do so much and do it so quickly, they actually do so using just 2 of these digits by convention 0 and 1. Indeed, you might know that computers only speak the so-called binary system or language, otherwise known as base 2. But just by using zeros and ones can you represent in binary, so to speak, any piece of information in the world. So let's consider how we might actually now do this. Let's consider how we might actually now do this using these zeros and ones, otherwise known as bits, for binary digits. All right, give me 1 second. Computers only speak binary. OK, so why is it that computers only speak binary? Well, at the end of the day, what is it that you do, no matter the device? At the end of the day, what is it you do in order to use your device next time? You plug it into the wall in some form to charge it using electricity. So at the end of the day, the only physical input to your phone, your laptop, your desktop is that socket in the wall and the electrons or whatnot that are flowing in and out. So if a computer really then can either be on or off, it turns out that by using electricity, just thinking here, I think we're spending too much time belaboring this point. All right. So how is it that computers, we'll rewind and redo that. So how do computers represent these zeros and ones? Well, inside of your computer are thousands, millions of tiny little switches, otherwise known as transistors. And these switches can, of course, be either on or off, just like a light switch on the wall. Now, if you have just one switch that can be off or on, you can't count particularly high. For instance, here's a light bulb that has a switch, and it's currently off. And so we could just arbitrarily, as humans, agree that this light bulb here represents a 0 because it is off. But if we allow some electricity to start flowing, either from the wall or a battery, this light bulb now is representing the number 1. And so this thing has a switch. I can turn it on and off, and therefore count from 0 up to 1, but that's it. But that's information. I can remember whether the lights are on or off or any other piece of information using this bulb. But how do I count higher than 1? Well, I would seem to need a second light bulb. OK, so if I want to count from 1 to 2, I could turn on a second bulb. And if I want to count from 2 to 3, I could turn on a third bulb. But how do I count even higher than that? Well, I'm going to need to grab some more light bulbs. But not necessarily. This, again, is unary, where things are either on or off, and I'm just turning them on in one direction. But I bet I can count higher. In fact, does anyone know from the audience here, how high could you actually count with a human hand with 5 fingers? It turns out that you and I can count higher than 1, 2, 3, 4, 5. Anyone want to propose what the answer is? Feel free to message Carter Zenke, Carter, in the chat. And let's see if we can't get an answer. Ironically, pretty much everyone has raised their Zoom hand, which is actually the right answer, to counting in unary 5, but if you're using binary instead or another scheme, Carter, can we test going to you to see what the most popular answer might be? Carter?
Sure, I'm seeing 32, 15, 16.
Yeah, so
36.
several answers there, and it turns out that, let me toss Carter on the screen here, but it turns out that with just a single human hand with 5 fingers, you can actually count as high as 31, because you don't have to just count from 1 to 2 to 3 to 4 to 5. You could maybe say that this is 1, maybe this is 2, this could now be 3, this could be offensively 4, this could be 5, this could be 6, this can be 7. In other words, if we take into account the ordering of the fingers, can we also count much higher than that? So let's see how best to do this. I don't think we're going to do that. I think we'll shorten that. So let's consider how high we might count using binary. Da-da. Yeah, wow. Are you going to be able to see this, Ian, on screen? If I stand here? Wow. OK. OK, just working. Oh, wow. Oh, even over here. I mean, they're deliberately dimmed, but it's really hard to see. I can try to brighten them tonight, though. All right, so let's consider the following scenario. Suppose we have 3 light bulbs or 3 switches. How high can we count? Well, let's initially turn them all off, like here. And if we turn just one on, this could be 1. This could be 2. This could damn it, that's the wrong one. Let's do that again. With all the light bulbs off, let's see how high we can count. This might be 0. This might be 1. This might be 2. This might be 3. This might be 4. This might be 5. This might be 6. And this might be 7. So with 3 bulbs, can I apparently count as high as 7 so long as I take into account which bulbs are on and off and not just the total number of bulbs that are on and off. Now, why that pattern? Why that pattern that I just called out? Well, it turns out that computers use binary in exactly the same way that you and I use decimal. But they only have these zeros and ones. But let's consider in our decimal world, how is it we get from these symbols to the numbers you and I know and communicate with? For instance, this. This is, of course, the number 123. But why is that the case? Really, all I see is 3 symbols. Something we call a 1, something we call a 2, something we call a 3. But you and I instinctively assign meaning to the positions of those 3 symbols when written here as follows. In fact, recall that you might have learned mathematics early on is the 3 being in the so-called ones column, the 2 in the tens column, the 1 in the 100s column. And how do we then get from 1, 2, 3 to 123? Well, it's like saying 100 times 1 plus 10 times 2 plus 1 times 3, which of course gives us 100 plus 20 plus 3, or 123. So that's decimal, and you and I all do this instinctively these days. But what if instead we took away most of those digits, 2 through 9, and left ourselves with just zeros and ones? Well, notice the pattern we just followed. We had 3 digits, or placeholders, the ones place, the tens place, and the hundreds. Mathematically, it turns out that it's 1 and 10 and 100 because these are each powers of 10. 10 to the 0, 10 to the 1, 10 to the 2. And it's 10 because we're using decimal, dec meaning 10, because we're using 0 through 9. But if we instead use 0 and 1 only, our base is no longer 10, but simply 2. So it turns out that computers, insofar as they only use zeros and ones, they use a ones place that's 2 to the 0, a twos place that's 2 to the 1, and a fours place that's really 2 to the 4. So the columns or places mean something different, but the mathematics and idea is exactly the same. So for instance, if these are now our columns, 1, 2, 4, and if we keep going 8, 16, 32, 64, how do we now represent numbers just like I did with those light bulbs? Well, this pattern of bits, binary digits, 0, 0, 0, of course, still represents in binary the number 0 that you and I know in decimal. Why? 4 times 0 is 0. 2 times 0 is 0. 1 times 0 is 0. Add them all up together. What do you get? 0. But how would a computer represent then the number 1? Well, if that computer has 3 switches, 3 light bulbs, if you will, it would turn on just the rightmost of those switches, thereby storing a little bit of electricity in the pattern 0, 0, 1. If you want to represent the number 2 in a computer, a different switch would turn on, this one would turn off, and you would have the pattern 0, 1, 0. If you wanted to represent 3, 2 switches now come on, those 2 specifically, because this is 2 times 1 plus 1 times 1, or the number you and I know as 3. Now, if we count up to 4, we have to change all 3 of the switches so that it's now 1, 0, 0, which is not 100. That's decimal speak. This is 1, 0, 0 in binary speak. So 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 would be 7. Now, how, of course, could we count up to 8? We'd need another bit or light bulb. We need another switch. And indeed, as computers have gotten newer and more modern, they have more and more switches, more and more of these transistors. And that's why today's computers, among other reasons, can do so much more than they once upon a time used to be able to do. Well, let's go to the audience now and ask a question. If all computers can count in are zeros and ones, we seem pretty covered that computers can do things like math and programs like Excel that really tend to store numbers alone. But if we only have zeros and ones, or light bulbs, if you will, how can we go about representing something like letters? Carter, could we proxy someone's thoughts or call on someone outright? How can we represent letters? This is where I have to go over and turn Carter on.
I see some people saying a general art of making patterns and maybe something with bits. And I see some use of the word ASCII.
ASCII. So that's indeed the answer, even though we haven't spelled out what it means. But indeed, humans years ago decided that if at the end of the day all computers can do is store bits, zeros and ones, well, let's just agree further on certain patterns of zeros and ones representing letters of, for instance, the English alphabet. And so long as all of us agree what those mappings are, we can now intercommunicate not just in numbers but in text. And so, for instance, what humans decided years ago is that a capital letter A in the English alphabet shall be represented with the decimal number 65. In binary context, that is what the computer itself would store in order to represent a capital letter A, it would store this, 0100, 0001, which if you do out the math, with more than 3 switches this time, a total of 8, that would indeed give you 65. Now, how does this work? Because this pattern, going to get used to this, this pattern of zeros and ones here would seem to represent the number 65, and yet I claim it can also represent the letter A. So how does the computer know which one to show you? How do you, the human, with your eyes, decide whether this represents a number or letter? Well, it turns out it's completely dependent on the software that you're using. If that pattern of zeros and ones were being used by a computer in a program like Microsoft Excel, it would probably be interpreted as a decimal 65, and that's what you, the human, would see. But if that same pattern of zeros and ones was being stored in like a Microsoft Word file or Google document, what you, the human, might see is actually a capital letter A. So it's completely dependent on the context in which those zeros and ones appear. And you, as a programmer, ultimately get to decide how to tell the computer to display any one of these patterns of bits. All right, well, what comes after 65? Well, 66, of course, and it turns out that this world invented ASCII, the American Standard Code for Information Interchange. And this is just a mapping between all English letters of the alphabet plus some punctuation 2 and corresponding numbers. So for instance, 66 would be B, 67 would be D, 68 would be D, 69 would be E, and so forth. And so for instance then, if your computer were to receive in the form of an email or a text message, how about this pattern here, 72, 73, 33? What message would you have just received via email or text? 72, 73, 33. What message would you have received? Feel free to message Carter again in the chat. And Carter, let me throw you up on the screen here to say quite simply what it is we have spelled.
Hi.
Exactly, hi. So HI, but that kind of leaves open for interpretation. Whoops. That kind of leaves open for interpretation. What? Can't get rid of Carter. Give me a sec. That kind of leaves open for interpretation what this 33 is. Well, it turns out you would only know by looking it up or having seen it before. It turns out that there's a whole chart that associates these numbers with letters, that chart known as ASCII. And indeed, here's a screenshot thereof, you can see 72 is H, 73 is I, and if I now look for 33, there it is, an exclamation point. And so that's what a computer is ultimately doing when sending you a message via text or email or the like. So I think along the way here, just for context, I think we would ask a few questions, but ultimately we would now move on to other representations of characters. So what is it your computer has actually received? Technically, yes, the numbers in decimals 72, 73, 33, but be it a wireless signal or something electrical on a wire, what you really received was these patterns of zeros and ones. Indeed, if we did out this math, we would get 72, which is H, 73, which is I, and 33, which is this exclamation point. So why did I use? You'll notice that for each of these letters, I actually took care to use 8 total bits, even though the leftmost of these bits, the ones all the way to the left, were 0. And much like in our human world that uses decimal, it typically doesn't matter if you put 0 and 0 and 0 to the left of any digit. For instance, 123 is the same as 0, 123. It's really, those leading zeros don't matter. But it turns out that this is convention by computers to use a standard or fixed number of bits in clusters so that it's always obvious where the boundaries are between letters. For instance, suppose that you had received 101. Did you receive a 1, a 0, and a 1? Did you instead receive a 10, which is 2, and a 1? Did you instead receive a 1 and another 1? We won't do that example. And this unit of measure, 8 bits, is what you might otherwise already know as bytes. And indeed, a byte is just a collection of 8 bits. A single collection of 8 bits might not be typically very helpful in general, and this is why we instead hear more often things like kilobytes, or thousands of bytes, megabytes, or millions of bytes, gigabytes, or billions of bytes, or even terabytes nowadays. And now a question via Carter.
We had some people asking, given a certain byte, how do we know if that's representing a number or an ASCII character?
A really good question. And in this case, again, it comes down to what program the human is using. If that pattern of zeros and ones is being used in the context of a spreadsheet, odds are it will be displayed as a number. If it's in the context of Microsoft Word or a Google Doc, odds are it will be displayed as text. By contrast, if you're using Photoshop, that same pattern of ones and zeros we'll see might actually be interpreted as a color of the rainbow. It entirely depends on those tools. So it turns out that if we standardize just how many bits we use to represent letters of the alphabet, you can use them to spell out entire words and messages, not just single characters alone. In fact, on this stage here are 64 total bits or light bulbs that might very well be representing something in ASCII if you consider the first 8 and do the math, and the next 8 and then do the math, and do that 6 more times, you might very well have an 8-character message there. But of course, this is very American-centric. All of the letters of the alphabet and the words we've seen thus far are in English, and that's indeed because of the people who first created it, but there's so many other written and spoken languages in the world, certainly as well. And indeed, even on a keyboard are there symbols that might not be as easily typed, but they need to be used to represent certain symbols in other languages too, such as those pictured here. And you might have even seen, popularly now, these kinds of pictures or pictograms, which it turns out are really just characters, patterns of zeros and ones that happen to be displayed by your Mac and PC and your phone as pictures, but these too are really just patterns of 8 or 16, maybe 32 zeros and ones. And so this pattern of zeros and ones is what's otherwise known as Unicode now, because it turns out within humans years ago used only 7 or technically 8 bits in order to represent letters of the alphabet. That means that if you have 8 bits or zeros and ones, that's 256 total possible letters, which is plenty for English, but it's not nearly enough for so many other languages around the world, particularly those that have many more symbols than A through Z. And so Unicode uses not just 8 bits, but maybe 16 bits or even 32 bits to represent many more letters. So in fact, a little bit of trivia. If you were to receive a text message with a pattern of zeros and ones representing 4,036,991,159, what character have you just received from someone? Ironically, Zoom does not support emojis in the chat window, so no one can actually answer this in textual form. But it turns out that same number would be this pattern of zeros and ones, 32 of them total. And it's perhaps apt that what that pattern of zeros and ones represents would be exactly this emoji here. Pictured here is Google's version, and here's Apple's version of the same. So anytime you send or receive these emojis, you're just sending this sequence of zeros and ones, somehow electrically, somehow wirelessly, that are received by your friend or someone else. And your phone, your Mac, your PC is displaying those patterns of zeros and ones according to Unicode based on what they actually represent. And in fact, one of the reasons for the proliferation of emojis is that when you have 32 bits, that's a lot more possible permutations of zeros and ones, and we just have a lot of room for this. And can we now ultimately represent, ideally, all of the human languages, if not emotions as well, of the world? All right, I think here, too, we would pause to take a question or so. And in fact, Carter, feel free to interject if there's some common theme we should address. Oh, did I see Carter about to pop on? No? No? OK, well, do you want to just, let's see. Oh, we didn't. Oh, that's interesting. There we go. So there was a bit of delay there, Rongshin. Was that, do we know why? I saw him on the monitor immediately, but it took a few seconds to appear there. OK, maybe there's a delay. Carter, do you mind speaking? Oh.
Yeah, I'm here.
OK, that was pretty immediate. Say it, Carter, speak again.
Hi, here on stage from 125.
OK, so it's like a 1 second delay. All right, back to the class. So now we're at the point of using just zeros and ones to represent numbers and letters. But how do we represent something more, like the actual colors in these pictures? For instance, this dot here is but a shade of yellow. How might a computer represent this? Well, it turns out that years ago, much like with ASCII and Unicode, humans got together and decided to standardize in one way or another how computers represent colors. And one of the more popular ways is using this RGB, some amount of red, of green, and blue. And so long as you use some number of bits to represent how much red you want on the screen, how much green you want on the screen, and how much blue you want in the screen, all in the same place overlaid on each other, that can ultimately give you any color of the rainbow. So for instance, suppose that your computer were storing a pattern of zeros and ones that, if you do out the math, represents in decimal 72, 73, 33. If you were to view those zeros and ones in a Word document or a text messaging program, you would see, as Carter said, hi on the screen. But if you instead tried to view these same zeros and ones, and probably many more too, in a program like Photoshop, you would actually see that shade of yellow. Why? Because the computer would interpret this as being, give me 72 amount of red, 73 amount of green, and 33 amount of blue. And when those three things are combined by a computer, you indeed get this shade of yellow here. And you can actually see this single yellow dot or pixel on certain screens nowadays, like your phone or your laptop. For instance, consider this emoji from before just opened at roughly its normal size. Let's zoom in a little bit. Let's zoom in a little more. And you can start to see, once you zoom in enough, each of these individual dots or pixels. And each of these dots are using some amount of red, some amount of green, some amount of blue to give us the shade of yellow, of white, of black, and of brown, and every other color in this particular shape. And so what that means is that each of these squares here is storing So what that means is that each of these squares here is using as many bits as are needed to represent 3 different values. And by convention, computers use 3 bytes, one for red, one for green, one for blue, which is to say that each of these dots represents 3 bytes. And so if you've ever stopped to wonder why the photographs you take with your phone are so many bytes, so many megabytes, that's because they're composed of so many dots or pixels, and each of those dots or pixels themselves take 3 bytes. So if you multiply all of that out, you get very large files for the same. All right, and then if we wanted to represent not just pictures, but we also wanted to represent something like, let me pause here. I think when we have more screens, I think, would you agree we'd be interacting more like we did last fall? I'm just trying to figure out pacing here. I think when we have more screens and we would, I think, interject with more questions, because I feel like I'm doing most of the talking here. Okay. And let's try this, just so we can run through the paces. There's very bright lights in my face, which is why I'm currently doing this. Can we put Baber? Would you like to, do you have a question at hand? Rangshin, could we pin Baber, B-A-B-E-R? Yeah, Baber, what's on your mind?
Yeah, so you mentioned how numbers were represented, characters, punctuation, colors. I was curious how sound is represented, because there's an element of analog there, I guess.
Indeed, what a perfect segue. So I think in an ideal world, Baber, I would take that question in like 30 seconds. Let me come back to that in just a moment, because it's perhaps a little more apt that we first ask one other question. Given all of these images, how might you represent videos as well? Well, it turns out that most videos are really just a sequence of pictures, but so many pictures changing so quickly that what you see is ultimately the illusion of motion. In fact, if you've ever heard of a movie being 24 or 30 frames per second, that essentially means you're seeing 24 or 30 pictures per second flying by the screen, and your human eyes and brain interpret it as fluid movement. In fact, you can see this even as a kid. If you ever read or even made one of these little flip books, which I'll play on the context of the screen here. Here, for instance, is an example of exactly the same idea, but in physical form. And you might, let me see how we do this transition here. You might wonder next how you're actually representing sound, for instance, like these musical notes here. Well, it turns out that computers can represent sound in any number of ways. For instance, each of these musical notes on sheet music represents a note, for instance, A through G, or sharp or perhaps flat. But you could perhaps store not just the note in a computer using some pattern of zeros and ones, but also the duration of each note and the volume of each note. And using that information, could a computer then synthesize this song? Alternatively, you could use a standard file format like MIDI, M-I-D-I. And those of you who are musicians might have used this format to load or save music that you yourself might have created. For instance, here, all of these decimal numbers, if loaded into the right software, would actually play a song as well that tomorrow I would hit a key on my keyboard, and then we would hear audibly as well. And so these are just some of the forms of information that you and I can store using a computer, be it, again, a number or text or image or video or sound or anything more. And so I dare say we have more than enough ways now to represent information or our inputs and outputs. How do we now represent the problem-solving process in between, otherwise known as an algorithm? An algorithm is just step-by-step instructions for solving some problem. And you and I execute algorithms every day, even if you might not think of them as that, but sets of instructions that allow you to take as input some problem and produce the solution. So for instance, let's consider a problem that you might solve occasionally. Anytime you go to message a friend or call someone on the phone, you might pull up your contacts on your iPhone or Android device or the like. And those contacts are probably sorted alphabetically from A through Z, for instance. And you might then start to search for your friend, maybe by scrolling, but if you have a lot of people on your phone, you might instead use autocomplete and start typing one or more letters and let the phone search for that person for you. Well, it turns out this is what we humans have been doing for years, even though this technology, an old school phone book, isn't very much in vogue nowadays, but this is just a problem to solve. If I wanted to search for someone's number, like John Harvard in this here phone book, well, I could start at the beginning, looking for him one page at a time, and then I might eventually make my way to the J section, in which I see, there is John Harvard. Or I could do it a little more quickly, just because I'm quickly getting bored, and I could do 2 pages at a time. So 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, and so forth, being twice as fast. So that would be a different algorithm, doing 2 pages at a time. But let me ask the group, would that algorithm be correct too? If I'm looking for John Harvard and I go 2 pages at a time just to speed things up, would that be correct? Would that be correct? So I think here what we would do typically, Akshat, can we go to you? Rangshin, A-K-S-H-A-T. I'm just helping a colleague find the names on the screen. Yeah, Akshat, would that algorithm be correct?
I mean, yes, sir. Sir, if we think about that, then there are chances that might be the name is between the pages, like the name you is given the page.
Indeed, the name might actually be sandwiched in between the page. And I'll notice, even over Zoom, we can all see your fish there. So nice to meet you both. So you might indeed find yourself in a situation where John Harvard is sandwiched between two of these pages. And so that would actually be a mistake or a bug. A bug is just a mistake in an algorithm. And indeed, I might blow past John Harvard here and decide, oh, he's not there just because I missed him. But I could fix this. I could perhaps double back one page, and voila, then find John Harvard. So long as I realize that if I go a little too far, I might hit a name that starts with K instead of J, I could double back at least one page and just make sure, as Akshat said, that I didn't actually miss him. But of course, we can do this even faster. I can go, for instance, roughly to the middle of the phone book, just aggressively so, and say, I definitely went too far. I'm in the M section. But at this point, I can both figuratively and heck, literally tear the problem in half, throw half of the problem away, leaving me with maybe not 1,000 pages, but 500 pages alone, maybe the A's through the M's. And now if I want to search for John Harvard, I can search here halfway through, and a little too far. Now I'm in the K section, and so I can again throw half of the problem away. And I can repeat this process again and again, effectively dividing and conquering, if you will, until finally I end up with just a single page on which John Harvard's name and number hopefully is. Now, why is that important? Why is that important, or why is that compelling? Well, it turns out we can give some thought now. I got to remember to toggle back to that, as to just how much better that third algorithm was. For instance, here's an XY plot. On the x-axis is the size of the problem. So the farther we go out this way, the bigger the problem, the more pages in the phone book. On the y-axis here is the time to solve. So the higher up here, the more time, the more seconds it's going to take to find someone like John Harvard. So what's the relationship between the size of a problem, or the size of that phone book, and how long it takes me to solve a problem? Well, it turns out it's pretty much a straight line. If a phone book has n pages, n representing number, then it's a one-to-one relationship between pages in the phone book and the number of seconds. Because with each additional page, it might take me one additional second. But the second algorithm that Akshat critiqued allowed me to go 2 pages at a time, which is technically twice as fast, even though I might have to double back a page or so. And if we compare these two for the same size phone book, notice that this algorithm here, my second in yellow, might take this many seconds. But my first algorithm might take twice as many seconds because, of course, I'm going 1 and not 2 pages at a time. But that third algorithm, if I do this the third way, dividing and conquering in half and in half and in half, not taking 1 byte or 2 bytes at a time, but like 500 bytes and 250 bytes and so forth, that analysis is going to look a little more like this. It doesn't actually get flat, but it rises so much more slowly. And so even if the local phone company gives us a much bigger phone book next year, not a problem, because even as the phone book gets bigger and bigger, the amount of time to solve the problem doesn't increase as quickly. Why? Because I can still tear the phone book in half just one additional time in order to find the person I'm looking for quickly. So now we're kind of programming. We're programming, albeit verbally, but let's start to formalize this a little bit. Before we get to C, before we get to Python or any other language, let's talk about pseudocode. A language that's not formalized. You just use English or any human language just to express yourself succinctly and precisely. So here, for instance, might be pseudocode for that third and last algorithm. Go ahead and pick up phone book, as I did as step 1. Open to the middle of the phone book, which I did as step 2. Look at the page, as I did in line 4. If person is on page, John Harvard in my case, call person. So I didn't get that far until the very end, but I'm checking, because if I got lucky and I opened the phone book and boom, he's there, I could have just called right then. But if the person is earlier in the phone book, to the left, well, what I did was this. I opened to the middle of the left half of the phone book, and then I went back to, essentially, line 3. And herein lies that same idea again of a loop or a cycle. I can just repeat myself again and again, but in this case, I've made the problem smaller each time I repeat. Else, if the person happens to be later in the book, same thing, but the other direction. Open to the middle of the right half of the book and then go back to line 3. Lastly, there's a fourth scenario. Now, John Harvard hasn't lived in Cambridge for some time, so it's possible he's not there, in which case else we should just quit. Because if he's not on this page or earlier or later, John Harvard is just no longer in this phone book. So that then is pseudocode, just one way of expressing this algorithm. But it's representative now of some ideas we're going to start to see in actual programming languages today and beyond. For instance, highlighted in here in yellow are things we might call functions. A function is an action or verb, something that the program can do very specifically for you. Highlighted now in yellow are these conditionals, if, else, that are sort of like proverbial forks in the road. You're only going to do this thing if the answer to a question is yes. Well, what are those questions? Highlighted in here are what are called Boolean expressions. A Boolean expression, named after a mathematician named Boole, is just a question that has a yes or no, or more technically, a true or false, or heck, a 1 or 0 answer to it. And then lastly, highlighted here are what we might call loops, those same cycles that allow us to do something again and again. So even here, using a pretty familiar technology, or lack thereof in this phone book or phone, we have some general fundamentals of most any programming language today. Functions, conditionals, Boolean expressions, and loops. And I'm going to change this year, and we're going to start more precisely saying conditionals here. All right. But programming languages, as we'll see over the coming weeks, have other functions as well, including support for variables, like in math, something called threads and events that allow us to create even more interactive programs too. So the first program we might create, and in fact next week will create, is going to be this one here in C that quite simply is only going to print out hello world. But my God, look at all of the distractions. There's this hash symbol and these angled brackets and parentheses, curly braces, quotes, parentheses, and semicolons. It's more syntax than it is ideas. And so today and this week, we focus on another simpler language that has the same functionality at its core, but is so much more accessible and user-friendly. And in fact, so much so that you might have yourself have used it in middle school or high school or some time on your own, this language from MIT called Scratch, a graphical, block-based language that allows you to program by dragging and dropping puzzle pieces. And so in fact, let's take a quick look here at a program that a former student of ours themselves created. And now here, in advance, I'll have created this, have readied the screen over here. I'm realizing, give me a moment. I'm going to full screen this, and then I would more elegantly toggle over to screen 1 and do this. Language called Scratch, can we not only implement simple ideas, as we'll see, we can create entire stories or more. Here, this program by a former student is inviting me to hit press space, so I'll do that. Let's see what happens.
What's your name?
All right, and here I'll type in my name, thereby providing this program with input.
Hello, David. What to do? What to do? I know. Better be Ravenclaw.
Just arrived in your common room after a long day on the Hogwarts Express. Isn't it nice? Seems like a great place to settle down for a nap. Oh no, you fell asleep in the common room and slept for 20 hours. Hurry, get to class before they kick you out of Hogwarts.
Late already, David? You're so late, class has already ended. Usually, I'd expel students for such negligence. I'm feeling generous today. If you can answer these questions correctly, you'll face no consequences. How many unforgivable curses are there? Answer with a number, not letters.
Let's turn to the audience with your physical hand so I can see on the screen, in the world of Harry Potter, how many unforgivable curses are there? Is it 0 or 1 or 2 or 3 or 4 or 5? Please use unary. Do not use binary on your fingers because it's too hard for me to count. I'm seeing a whole bunch of 3s. Let's try 3. I'm going to type in a 3, and presumably there's going to be one of those conditionals checking the answer to this question.
What spell is used to levitate an object?
What spell is used to levitate an object? It's going to be harder to do this physically, but if you'd like to message Carter, let's see if you know the spell that is used to levitate objects or make them float. Carter, you're hopefully being inundated with spells right now, hopefully all good ones, and not any of the other 3. Have a more popular
I'm seeing Wingardium Leviosa.
All right, Wingardium Leviosa. Let's go ahead and type this.
What is the first of the 5 exceptions to Gamp's law of elemental transfiguration?
Okay, we got that right. And the last question here is, what is the first of the 5 exceptions to Gamp's law of elemental transfiguration? In the world of Harry Potter, there's certain things you just can't do magically. It would break J.K. Rowling's magical world, and they are formalized in these laws. Carter, are you seeing a most popular answer?
I'm seeing an answer that this was not in the syllabus.
This was not in the syllabus. Indeed, and admittedly, I did not know this until I Googled last night. But do we have anything that sounds correct? All right, I'll go with not in syllabus.
Ha. Vengeance is sweet. Goodbye, David.
All right, and that's game over. It turns out if you Google, a magician in the world of Harry Potter cannot make food appear. That's the first rule that you can't violate. So just by a show of physical hands here, that demo, I do worry, was a little long, even though it's super cute and fun. Should we keep this kind of demo, or should we skip this kind of demo tomorrow? Thumbs up for keep, thumbs down for eliminate. I'm seeing a lot of thumbs up. OK. So I'm seeing 1 very angry thumbs down, 2 thumbs down. All right. Well, this is helpful as a litmus test. Feel free to let Carter know your thoughts so we can distill them, not just on the screen. All right. So I think at this point, team here, what we would do is announce a break. And when we come back, we'll actually use this language called Scratch to create some projects of our own. But let's go ahead and take a 5 or so minute break here. And when we resume, we'll take a look at some code on the screen. All right, so we'll take an actual break now for 5 minutes so we can regroup here. Back in 5 or so minutes, everyone. Do we go, so my audio goes off at this point, Ian, I assume? And we're on like a wide shot? Okay. Can you put everyone's hand down? All right, we are back. Thank you for bearing with us. We were making a whole bunch of changes to the hardware behind the scenes. Let me see if my colleague Rangshin has the ability to put everyone's hand down momentarily. All right, and let me go ahead and toss us all on the screen over here like before, just to give us an opportunity to say hello. I see a bunch of faces and names here on the screen. Oh, they're all moving around pretty fast. Anna Veronica, I see you on the screen. Do you want to say a quick hello world to everyone and where you're from? Anna Veronica? A-N-A space Veronica. There we go. Oh, and we got to unmute Anna.
Hello.
There we go. Hello.
I'm from Venezuela, and I've been taking this course since 2020, I think.
Well, nice to see you and meet you on Zoom here. Welcome aboard. And let's see, who else do we have here on the screen? Can we go? Oh, I saw a wave. Let's see. M.M. Bilal, can we say hello to you? M.M. Bilal, M space M, Rangshin. Give us a moment to find you in the Zoom. Let's see. All right, there we go. You're full screened. If you
Hello, sir. Hello, sir. Is it a great pleasure to see you? Like, I have been following you for like 3 to 4 years, and I'm taking the CS50 every year just to get the chance to meet you. And it's really great, a pleasure. And I really want to thank you that I started my journey from your CS50 courses straight from Pakistan. So I'm really thankful to you. Thank you so much for everything you're doing. And I wish you best of luck and keep doing the good work. Thank you so much.
Well, thank you. I'm glad you could join us. And it must be getting late there today. Oh, I'm starting to hear a reverb. Yeah. Is that intentional? Testing one. Testing 1, 2. There we go. We're back. All right, how about time for one more hello on the screen here? Who do we have moving their hand so I can see? Let's see. Darius, do you want to say hello? Darius? D-A-R-I-U-S, Rangshin? OK, Darius, you are on the internet.
Darius, it's my pleasure to be here with you guys. I'm just starting to, study programming.
Well, welcome. Glad you could join us, too. And I hope you won't mind. We can't get to all several hundred people. We got to do a little more computer science. The goal now is just to dive into the more programming side of what will be tomorrow's lecture. So those of you who have been programming for some time might know this already, but give us just a moment to resume. We'll start in just a moment. Can we lower the audio for a second? All right. So at this point, for content, that's OK. All right, so we'll just have come back from break tomorrow, and the goal now is to dive into Scratch. So Scratch is a graphical or block-based programming language from MIT's Media Lab that indeed allows us to program by dragging and dropping puzzle pieces that are only going to interlock together if it makes logical sense for them to do so. And let me introduce you then quickly to the world of Scratch, which can be used on any Mac or PC in a browser. This then is scratch.mit.edu. And there's just a few areas of the screen with which to become eventually familiar. For instance, here at the left is a whole palette of blocks or puzzle pieces. functions. These are the functions, the conditionals, the loops, and more that we're going to use to ultimately program by dragging and dropping. In this middle area is where we will be dragging and dropping those puzzle pieces and interlocking them in order to make something happen. That something is often going to be by way of one or more sprites, such as this Scratch himself, which is a cat, and is the default image, is the default character in the world of Scratch, but we can change Scratch to a dog, a bird, or anything else that we might want. And to do so, we should just be cognizant of the world in which Scratch lives. If you're, as you might recall from math class, we can associate, let's see, as you might recall from a math class, we can associate numbers with a grid like this. So in Scratch's world, he can move up and down and left and right. But how far can he move? Well, there's hundreds of pixels or dots on this screen. And at the moment, the cat is at location 0, 0. His x position, so to speak, is 0, and his y position is also 0 as well. If he goes up, straight up, he might go as high as y equaling 180. Or if he goes all the way down, it might be negative 180. So there's 360 pixels or dots top to bottom. Meanwhile, if he goes right or left, he can actually go a little farther. He can go to x equals negative 240 or positive 240 as well. Now, most of the time, we're not going to really care where Scratch is at x or y, x this or y that. Rather, that's only going to be applicable if we want to detect where he is in his world. So let's go ahead and do perhaps the simplest of Scratch programs here in an actual browser. I'm going to go ahead and create that same Hello World program from before. Now, at first glance, there might be quite a few puzzle pieces or building blocks here that you've never seen before, but honestly, they all say what they mean. And so just by poking around and experimenting, should it become clear what it is you can do with this tool. So I'm going to scroll down, in fact, to events, because I've done this before, and I'm going to focus on this block first here, when green flag clicked. When the green flag is clicked refers to Scratch's world over here at the right. Notice that there's this green flag indicating start, and this red stop sign indicating stop. That's going to allow me to start or stop, of course, my program. So when I start my program by clicking that green flag, let's do something super simple at first, something like making the cat look like it's saying hello, world. So I've gone ahead and connected these two puzzle pieces, which again are the right shapes so that they interlock. And now what I'm going to do is click that green flag. And voila, I've written a program. It's not a particularly impressive program, but it has taken as input my code, and it's produced as output hello world on the screen. Let's go ahead and do one slightly more sophisticated version. It turns out that a sprite, or Scratch in this case, can sense if maybe you've typed something in at your keyboard. So notice there's this puzzle piece here, ask what's your name and wait. But the fact that it's in a white box means there, or a white oval, means I can change the sentence, the question, to anything I want in any language for that matter. But I'm going to go ahead and use the default. And now notice I don't want to just append it to the bottom of this program, but notice that magnetically it kind of wants to connect. I'm going to go into the middle here and first ask the human what's their name, and then wait. Now, instead of just saying hello world, I'm going to go ahead and say this, hello, comma, and now I'm going to go and grab another looks block. I'm going to grab another say block, and I'm going to then go down here to sensing, because notice that the ask block is a little special. It doesn't just come with this ask block, it also comes with an answer block, which we're going to start calling a return value. Some functions, it turns out, can hand you back a useful thing like an answer like this. So in fact, I'm going to just go ahead and overwrite that default hello exclamation point and just have the program say hello, comma, and then answer. All right, I'm going to go ahead now and click stop, and now the green flag. Notice that I'm being prompted by the cat, what's my name? I'm going to type David, and voila, David. Well, that's a little rude. I didn't actually see a hello. Let me try that again. When in doubt, sort of reboot. So let me hit stop, start. All right, I'm being asked for my name, David, voila. Well, that too was rude. So what's actually happening here? And here with an in-person audience, I might pause for a moment, get folks to think about what it is that's going wrong. All right, so it seems that my Mac is just really fast. And so it's saying, hello, comma, David, but so fast that all I actually see ultimately on the screen is David. So I think I want to finish this thought all at once. So how can I combine hello and answer? Well, turns out if we poke around, there's some other puzzle pieces. Let me go under operators, and let me go to join, which by default kind of curiously says apple and banana. Those are just placeholders in English. You can change them to any two things we want. So I'm going to go ahead and change this to be saying hello, join apple banana, but that's going to look kind of stupid. The cat will say apple banana. Let me instead change apple to hello, comma, space. And now let me go back to sensing and grab that same answer puzzle piece that I threw away a moment ago and plug in answer. So now the cat is going to take now it's going to take multiple inputs, hello and this answer. It's going to join them together and then voila, say those things together. Let's try it. Green flag. Type in David and enter. Aha. Hello, David. So that was admittedly my first bug, my first mistake. Well, at least my second, minus 2 points, if you will. But now we have, it seems, a working program. But it turns out that this program actually fits our mental model from before and is representative of pretty much everything we're going to do in code henceforth. This thing here, again, might be called a function. Why? It's an action or a verb. It's just something built into the language, Scratch in this case, that does something specific, like, say, whatever's in the white box. Notice, though, that we can fit it to the same paradigm of input and output, where this time the input might be initially in version 1, hello, comma, world. Now that I think about it, I'm going to show this picture after the first example before we do the join. Hello, world is being fed as input to some algorithm. Well, the algorithm is just step-by-step instructions for doing something. And MIT has taught Scratch how to do something like say something. And so the input to the say function is hello, world. The output, of course, is the cat doing just that. The second version of my program now, which I think I would do live and then come back to this, introduced a second function, ask. But this function's a little different. It doesn't just say something. It kind of hands you back something reusable. We'll call it a variable, or more technically, a return value that you can reuse on subsequent parts of your code. So for instance, this fits into the paradigm as follows. What's your name is the input to the ask function. The ask function, of course, is the algorithm, step-by-step instructions that MIT figured out for asking a human something. The output is an answer. The return value, so to speak, is the answer that the human typed in. But notice what we can do. Because we got that answer, we can use it in a different way. Whoops, something's flying by. OK, so here. What did we then do with that answer? Well, recall that I nested one block on top of another. So it turns out that some functions, like join, can take not one, but two inputs, if you will. So if we depict this, we have a picture like this. Hello and answer are the two inputs to an algorithm called join, or to a function called join, the output of which is hello, comma, David. But notice now, that was then plopped on top of the say block. So this output, if we move it over, can become the input to another function. You can kind of chain these things together so that the output is, again, hello, comma, David. So again, it all boils down to input and output, and some algorithm in between. All right, so at this point here, what would we do? And this can escalate quickly. We can do much more interesting programs than this, even within this graphical world of Scratch. For instance, allow me to go down to this menu here. And let me just remember where I'm going. So let me go ahead and enable some text-to-speech in the world of Scratch. Oh, thank you. If only there were oh, that's Carter. So let me go ahead and import this text-to-speech capability of Scratch, and let me go ahead and do this. Instead of saying hello, answer, let me go ahead, oh, that's interesting. That disappears fast. Let me go ahead and now do this. Let me go ahead and speak something, but not just speak the default, which is hello. Let me go ahead and grab that same join block again, because I accidentally deleted it. Let me change apple to hello, comma. Let me grab the return value called answer and plop that in here. And now, if this works, crossing my fingers as always, I'm going to type in my name.
Hello, David.
So it's a different voice in this world of Scratch, but it looks like I can change that too based on what I've seen. Now we have a third version of the same. All right, so let's see if we can't now introduce some more sounds, but this one local to my computer and not necessarily using some fancy speech-to-text algorithm. Let's actually turn Scratch into a cat. Let me go ahead under sound here, and let me go ahead and just play a sound called meow until done. Scratch indeed comes with a whole bunch of cats and dogs and birds and more, as well as some associated sounds. So I'm just going to use the default meow sound here until done. Clicking the green flag. All right, so a very simple program that uses one function, play sound until done. Suppose I wanted this cat to be a little more lively and perhaps meow multiple times. Well, let me go ahead and grab a second copy of that block, maybe a third copy of that block, and let me hit play now. All right, maybe a lively cat, but maybe a hungry cat or unhappy cat. So let's have it at least wait in between here. Let me go under Control here and add wait 1 second in between. And again, if I hover just right, it will try to snap into place. And I'll do this again and again in between. And now let's see how the cat sounds. OK, perhaps still a little hungry, but maybe less aggressively so. But here I have a program that I'd argue is correct, but it's not well designed. And here already can we start the discussion of what it means not just to program, but to program well. It's one thing to do something correctly, like I did initially with the phone book, but it's another thing to do something correctly and in a well-designed way so that you solve the problem better. The better way with the phone book, of course, was to divide ultimately and conquer again and again. In this case, there's not really an opportunity to divide and conquer, but there is an opportunity not to repeat myself again and again. In fact, I essentially, in the form of these puzzle pieces, copied and pasted something I already did again and again, so I could do this 3 times. But you know what? Recall that from our pseudocode, there's these things called loops that might exist in an algorithm, and indeed in Scratch they exist too. So let me go ahead and fish around. Here's one. There's a repeat block. And notice this puzzle piece can kind of encapsulate other pieces as well. It looks a little tight, but it turns out Scratch will grow these things to fit whatever I want. Let me go ahead and drag this out here just for a moment. And let me go ahead and grab just one of these play sounds and put it inside. And let me grab just one of the wait 1 seconds, put it inside. And notice indeed the repeat block is growing taller and taller. Let me only do it 3 times, not 10. Let me go ahead and throw all of this away, which you can just drag and drop off to the side and they'll delete themselves. But let me reattach this now to the one green flag clicked. And now if I click that green flag, nice. So same exact effect, but why is it better? Well, if I want to ever change this program to do it 3 times, and rather than 3 times, do it 4, or heck, even 10 times or 100, I just change it in one place. I don't have to copy and drag and do something again and again. I can make one simple change, and as such, it's a lot less vulnerable to me just making stupid mistakes, dragging something but not something else. And if I want it to wait a little less often, let me change it to 0.1 second, for instance, and click play. Again, imagine if I had multiple wait blocks and multiple play blocks, I'd be changing so many of these little white boxes again and again. But we can do more than this. The cat at the moment is still just kind of standing still. Let me go ahead and get him to follow me around. So let me throw those pieces away. And let me this time do something forever. Just listen for me forever, for at least as long as the program is playing. And let me do this. Let me go under Motion. And let me go to, let's go to Point Towards Mouse Pointer. And see what this does for us. And then let me go ahead and move, not 10 steps, which feels like a big jump. Let me just move 1 step or really pixel at a time. And let me now play this. Why is the cat walking toward, oh, wait a minute. If I move my mouse pointer, notice that he's following me. And indeed, pointing at me and then stepping forward 1 pixel. Let me speed this up to the default 10 and see what happens. Now the cat's much faster. And you can create this sort of strange situation where he's trying and trying to keep up because it's literally doing forever what it is that I actually said. All right, well, what more can I do? What are some other puzzle pieces with which I can build more interesting programs? Well, let me fast forward to what one of our very own students did some time ago using exactly this principle of following. This example here is called Diamond Catcher. And you'll see with a bit of sound and a bit of animation and the same principle, just forever following that mouse pointer, notice what we can do. I'm going to click here to start. And you'll see this bowl follows my cursor. And the goal is to catch these diamonds, which is pretty easy so far, though I'm being warned at the bottom to avoid rocks. They're starting to fall faster. Notice my points, though, are going up, so something's keeping track of my points. The diamonds just got smaller and more present. There's a rock I want to avoid. If I hit the rock, I think I lose points. There's a star. That seems like a good thing. My points are real. Damn it. Now the diamonds are really moving. And you can imagine that what the student did here was they changed just how long these things are waiting in between each other. And now it's really hard, but more things are falling at a time. And we could do this all day long. And in fact, every time I hit the rocks, my score is going to go down, 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 until I either win or lose. So things can, again, escalate quickly, but using these very simple principles. And just by adding a bit more sound, a bit more thought, a bit more of a story, can you really bring these things to life. But these points here, for instance, something was keeping track, positive and negatively, what my actual score was. So how might we do this? Well, let me go back to my editor here, and let me go ahead and do this. Let me go ahead and start from scratch here, no pun intended, give myself a wait when green flag clicked, and let me go under something called variables. Like in math, you have x and y that you can assign numbers to. You can do this in a programming language too. Let me go ahead and set my variable to 1 initially if I want to start counting at 1. And you know what? I'm going to give it a better name. I'm not going to call it my variable. I'm going to call it counter. Why? It's just better design. It's kind of lame to call your variable my counter. Sorry, no. To call it my variable. Tell me what it is. So I'm going to name it counter. And now I'm going to do the following forever. I'm going to grab this big puzzle piece here. I am going to say what the current counter is, maybe for 2 seconds. And to do that, I need to go back to variables. I'm going to drag my counter variable and say not, of course, hello, but literally the value of that variable. I'm going to now go back to control, and I'm going to wait for a second just to give myself some breathing room. And now, lastly, under variables again, I'm going to change counter by 1, which quite simply means add 1 to the counter. Now I'm going to hit play, and we seem to have now a counting cat that's counting a little slowly, but it's going to indeed count up and up and up, keeping track of what its count is, or maybe if you prefer, what its score is, using these building blocks. Well, now we've seen loops, we've seen variables. What if I only want to do something once in a while, or conditionally, so to speak? Let me go ahead and do this. Let me throw away all of this counting, but still keep around something forever. And when the green flag is clicked, let me go ahead and forever do this. Let me ask a question under control. If something, then do this. So here's a conditional. And notice in this little trapezoid-like shape, I need to ask a question. Under sensing, turns out there's a whole bunch of these trapezoids, and I'm going to, or whatever they're called, and I'm going to go ahead and ask this question. If I'm touching the mouse pointer, and notice the shape matches, even though the size certainly doesn't, but Scratch will fix that, and it will grow to fill. Let me go ahead now and play the meow sound only if the cat is touching the mouse pointer. So let me hit the green flag. Nothing's happening. That's not strictly true, though. Forever something is happening. It's constantly asking the question, is it touching the mouse pointer, the cat? Well, let's do that. So anytime I move my cursor over the cat, it plays the sound meow because it's like I'm petting the cat, if you will. Now, we can do this another way, for instance. Here's one version that I made in advance here. Excuse me. Here's one version I made in advance that does a little something more. Watch this. All right, spoilers. Here's another one I made, which is just going to forever meow on its own. But this cat, by contrast, does not like to be pet. And you hear a different sound instead. Well, how might this be implemented? Well, let's go ahead and see inside this script. And all I did was this. Instead of using just an if, a single conditional, I used what we might call an if-else block, which is more like that fork in the road. You can either go left or right. That is, you can either play the sound roar or play the sound meow. Well, once I have the ability to do something forever and ask questions conditionally, notice what I can do too. Let me go back to my palette here. I have another example I made in advance here. And let me show you the inside of this. It too is not very long, but it has a forever block. And it has some pen tools. So it turns out Scratch comes with the ability to draw things digitally on the screen. And it looks like when the green flag is clicked, I'm going to erase everything, just in case I was drawing already. And then I'm going to forever do this. Go to the mouse pointer. which is presumably somewhere on the screen. If the mouse is down, that is, you're pressing the button, then put the pen down on the paper, so to speak. Else, pen up. So this is making a correlation between my mouse being down and the pen being down. And so what does this mean? Well, let me go ahead and draw here, or let me go ahead and click the green flag and click my mouse. And I'm now drawing on the screen. I've disabled the cat by changing its so-called costume. And indeed, if I go to costumes here, you'll see that the costume is white. It's blank. There's no cat. I literally just deleted it. But that's because the sprite in question, or sprites, don't need to be an actual cat or an animal. It can be any visualization thereof. Well, let's now add some more of that animation, a bit like the diamond game had just a little bit ago. Let's go ahead here and let me open up a program like this. Let me go ahead and open up a program called Bounce that initially does this if we look inside. This program, also quite small, first just sets rotation style left and right. And I figured that out by trial and error because, as you'll see, the cat was going every which way at first. But I'm going to forever have this cat move 10 steps, which is a pretty big jump. It's like 10 steps, like running at a time. But if the cat is touching the edge, a different Boolean expression, I want the cat to turn 180 degrees. So let me go ahead and hit the green flag here. And wow, so now the cat is bouncing back and forth, back and forth. But it's not quite like the cat is walking. It's kind of like literally the cat is bouncing, which is kind of lame. This isn't really animation. But it turns out that I could create the illusion of animation. Let me go under costumes here, which there's no costume here. Let me go ahead and open up a second version of this program called Bounce, version 1, that has a little bit more code to it. This version forever moves 10 steps, but it checks if it's touching the edge, then turn 180 degrees. But no matter what, change to the next costume. And indeed, if I go ahead and draw, or just import, as I did, 2 costumes for this cat. The default, which just has his feet stationary, and another one where they're slightly moved. I can toggle between these 2 costumes back and forth. And so the end result, when I click the green flag now, is almost the same, but kind of adorably, he's now running back and forth. Now, there's a lot of like flicker because you're only seeing 2 different versions of his feet. It's like a picture book with just 2 pages that are different. So it's not necessarily as smooth. But if I had 24 frames per second, 30 frames per second, like a proper video, we could really make this cat look like it's walking and not just bouncing. All right, so around here, I would ask for some questions, I think, because we have a few more examples to go. And Carter, as always, please do feel free to chime in. Let's go ahead now and see if we can't make things a little more. Oh, wait. Let's now take a look at what a student did using some of these same building blocks as their own project. I'm going to go open something called Walking Pavlov, a dog in this case, and let's see what he does. Oh, that's weird. There we go. Don't know what happened there. So notice, same idea, a little more movement in the feet, some cooler, hipper music playing, a nice costume on the stage and back to put the dog in the city. Notice that the student is counting how many times the dog has bounced. Apparently the dog has had enough, and now a food bowl comes in and end of scene. So again, taking some very basic primitives, but again, really bringing the creation to life and doing something much more animated in this case. Well, now let's try to see what more Scratch can do for us by doing the following instead. I'm going to open up an example that I also made in advance called Bark, and this one has a very annoying sea lion, if you will, but it's perhaps the most complicated of the ones as we've had here. But let's see what it does first. When I click the green flag, this sea lion starts barking again and again and again. And honestly, it does this forever. And it's one of the most annoying sounds of the world. If only there were a way to mute the sea lion by somehow getting the program to respond to my physical input. What might the solution be? Someone presumably yells out, keyboards, hit the space bar. And indeed, if I do that, the sea lion no longer starts barking. So the interesting takeaway here is not the sounds, not the forever, because we've seen all that before, but notice what I've done. In the first script here, as these things are called, I have a variable that I called muted. And I simply ask the question, if muted equals false, then start the sea lion, and then think hi, hi, hi for 2 seconds. That is, if muted is false, you're not muted, go ahead and play the sound. But notice this second script down here that's also listening for the green flag that sets muted to false by default, and then it forever just checks. If the keyboard spacebar is pressed, then change the value of this muted variable. Change muted from false to true. Sorry. Change muted from true to false if it's true. Else, change it from false to true, and then wait 1 second. And so in this case, you have an example of what a programmer might call threads. A computer can technically do multiple things in time. Multiple threads can be running on your computer at once. So one of these scripts might be barking and playing the sounds. The other might be listening for the keyboard, and they work then in conjunction. And indeed, when you saw the dog and the ball and the diamonds and the rocks and more, those were all different sprites, different scripts, and ultimately different threads, all doing something in parallel. Now, here's kind of a cool one, too. Notice what we can do if we introduce yet another library from scratch. And some of these I might not do tomorrow, but let's go ahead and do this one here. Let me go ahead and go back to my gallery. And instead of doing something when the green flag, let's go ahead and do this. Let me go ahead and open up the video sensing feature of Scratch. I'm going to allow Scratch to use my camera. I'm going to say when video motion is greater than 50, go ahead now and only now play the sound meow until done. Let me step off to the side. And now notice what you're seeing on the screen. All right, it's a little ugly there. Should we do this? Maybe I'll do that in advance. There's the cat on the stage, but now notice when I move my hand in front of my camera as though to pet the cat for virtually. I'm not doing it hard enough. There we go. OK. So not everything has to happen when the green flag is clicked. Rather, a program can be listening for these. OK, stop. can be listening for. Jeez. Oh, right. I got to stop moving. OK. Just throw it away. Problem solved. So not only does something can something happen when the green flag is clicked, you can also be listening, so to speak, for these other events too. All right, so now I got some music example. Do I want to do this? I feel like there's too many of these. Let's go through them, but we might nick some of these tomorrow for those of you following along at home. What if we wanted to create music too? Well, a computer can represent musical notes in different ways, and let's see how Scratch might help us do that. Let me go ahead now and get rid of the camera. Let me go ahead now, and when the green flag is clicked, I'm going to do this from memory instead. Let's go ahead now and open a program we wrote in advance called Music that if we take a look inside here, just plays a bunch of notes for some number of beats. OK, is that interesting? All right, we may or may not keep that one. It's a little Easter egg there. Do we want to do events? All right, what if, meanwhile, you want to have not just 2 scripts, but actually multiple sprites? Well, it turns out that you don't have to limit yourself to just 1 cat or 1 sea lion. You can have 2 cats, or in this case, 2 puppets. And so in this case, notice how this game of sorts is played. When I hit the space bar in this program, the puppet on the left says Marco, and the one on the right immediately says Polo. But it turns out the one on the right is only saying Polo because it heard the one on the left saying Marco. And indeed, if we take a look inside, notice this. If the key space is pressed, so if I press the space bar on my keyboard, then notice that not only does the orange puppet say Marco visually on the screen, it also broadcasts something called an event. And I can name this anything I want, but it's kind of like a way of passing a message from one sprite to another. And if that other sprite, the blue puppet here, if I click on its sprite here, all this blue puppet is doing is not listening for the green flag, it's listening for that event. It's listening for that message to be broadcast to it. And because the blue puppet is listening for this event, it can say Polo in response. So again, just another building block via which you can make increasingly sophisticated projects by having now some of our programs intercommunicate. All right, I did a translation one last time. I think we're going to skip that because it's dragging. So let's go ahead and take a look at one final set of simple examples before we really build on top of those. Let me go ahead and revisit this question of having the cat meow as follows. When the green flag is clicked, I want to go ahead and repeat the following 3 times as before. I want to go ahead and play the sound meow until done, and then I want to go ahead and wait just 1 second in between. Let's hit play. So this program is correct, and it's pretty well designed. It's hard to see room for improvement. But suppose that elsewhere in my program, I wanted to have another cat or another sprite meow, or do even something else. Wouldn't it be nice if I could write some code, that is drag and drop some puzzle pieces, that I could then reuse elsewhere? And indeed, you can do this in Scratch. You can create your own custom puzzle pieces by going under My Blocks, clicking Make a Block, and let me literally create a new puzzle piece called Meow, and hit OK. I now have this pink puzzle piece that defines something called Meow, and what I'm going to do is this. I'm going to just move the playing sound and the waiting over to this puzzle piece. And you know what? Now I'm done. I have invented the notion of meowing, and I'm going to just like scroll down and put this out of sight, out of mind, and scroll up. Because now, what do I want to repeat 3 times? Because I made a new block, I now have a pink puzzle piece called simply Meow that I can drag from the left. And so now this is an example of what a computer scientist would call an abstraction. The Meow puzzle piece now exists. Someone else, turned out it happens to be me, implemented it by dragging and dropping the right puzzle pieces. But you and I now, anytime we want something to meow, we can just use this abstraction, this simplification of those otherwise multiple steps. The program's going to work the same, but it's even more readable. I see that I'm repeating the meowing 3 times, and that's it. I don't have to think about what those other blocks are doing. But I dare say we could take this 1 step further. Functions, of course, can take inputs, and so can these custom blocks take inputs. So let me go ahead and do this. Let me go ahead and right-click on Meow and edit it, and this time add an input, some number of text, and let me go ahead and say n for number, and then let me just add some text so that it reads more like English, and say times. Now what have I done here? I now have a puzzle piece that doesn't just say meow, it meows some number of times. And so what I'm going to do is this. I'm going to get rid of this repeat block here. I'm going to scroll back down to my implementation of meow and actually put this loop inside of the block. And then notice, instead of hard coding 3, I'm going to drag a copy of this n. So now my meow block takes input 2, and it allows me to parameterize it, that is, control the behavior by repeating some specific number of times. And now way up here, notice how simple my underlying program gets. I just drag one puzzle piece, say meow 3 times, and boom, done. So again, still correct, but better designed in the sense that now it's even more readable to us humans. It's even more abstracted so that I don't have to worry anymore what it means to be to meow. And most importantly, it's reusable. I can meow again and again by using my new piece. Carter, question from the group.
I think some people are wondering, what's the difference between this define block and a variable? They both seem to be names for things, but is there a difference there?
Really good question. A define block defines functionality, so actual operations involving functions and loops and conditionals and more. A variable only stores a value. It stores data, a number, a word, or something else. And that's the distinction there. So now that I have this capability of abstracting things, let's go ahead and take a look at 2 final projects, one of which I myself made, not when I took CS50 itself, but in graduate school when I was cross-registered for a class at MIT. I give you Oscar time. This is a program now that invites me to drag trash over to Oscar's trash can, and when I get close to it, it pops up, and who pops out? Oscar the Grouch himself, keeping track of my score. I'll do it again and go hopefully from 1 to 2 points. The song's about to change. So now not just trash, but a sneaker is falling from the sky. And again and again. And much like the diamond game, does more and more trash fall at a faster and faster rate potentially, and so the game gets harder and harder over time. So how do you go about implementing something like this if you see something online that you want to model yours on, or you just want to build something, no pun intended, from scratch that's as dynamic and interactive as the ones we've seen here? The most important thing is to break down these bigger problems into much smaller ones still. In fact, the first thing I probably did at the time when making this program was literally this. a program that did nothing other than have a costume on the stage. There are no puzzle pieces here because my first version of Oscar Time did nothing, but I poked around online. I found this Sesame Street lamppost, and I plopped it on the so-called stage of my program so that I could just have this backdrop there. Well, what might I have done after that? Well, the next thing I probably did was I only focused on the trash can because this was a problem to be solved. Anytime I moved the cursor near the trash can, I wanted the lid to go up and then go down. So I didn't implement all of this at once. Rather, I did just this, a few puzzle pieces here. Oh, that's not the wrong one. Trash can. Uh-oh, it's missing. All right, I am missing one, but what I would have done, can I do this? I'm gonna fix this later. Carter, if you can make note for me to add trash can to the studio. So what you would see here is an example whereby I have the trash can only, and I move my mouse over to it, and as soon as it's touching the trash can using one of those if blocks, the costume would change, the trash can would go up, and as I move away, the opposite would happen too. All right, so at that point, I have a lamppost on the screen, and I have a trash can that goes up and down. What next? Well, let me figure out how to get some trash to start falling. And indeed, the next example that I probably did back in the day was just that. I implemented some falling trash like this. I picked, for instance, a random location using this other puzzle piece in green that picks a random location between -240 and +240 as before, and a y location of 180, which is all the way at the top. I then said the following. If the distance to the floor, and the floor is just a second sprite that I made that's literally living on the bottom of the screen, is greater than 0, then I change the y location of this piece of trash by -3 to move it down closer and closer to the floor. So the net effect is this. If I click the green flag, trash starts at a random location along the top, and then it goes until it hits that so-called floor sprite at the bottom. And notice if I drag it back up, it will just keep going all day long because of that forever block. So again, if I now add the lamppost and the trash can and the falling trash, we're getting closer and closer to Oscar time. What about this ability to actually move the trash? In retrospect, I shouldn't move the trash because that only works in editing mode. Well, I have another version here where I implemented the ability to drag the trash. I might ask the audience here how you might do it, but here too is an opportunity for forever. If the mouse is down and it's touching the mouse pointer. So if your mouse is down and the trash is touching the mouse pointer, then go to the mouse pointer. So you don't have to point at it just. You can literally go to it so that it follows you precisely. And indeed, if I go over here and click and then go up, down, left, or right, the trash follows me as though I have picked it up. So now there's a few things more that I would need to do. I need to add the music, which I probably spent way too much time on. I need to go in and add the shoe and a whole bunch more. But those same building blocks can ultimately yield the end result. And Carter, do we still have a question from Carter? I forgot to click that off. Nope.
Nothing here.
All right, so one final set of building blocks and one final game. One final building block and one final game. Let's consider a couple final primitives. Suppose that we wanted to create a game that allows us to move from side to side. For instance, pictured here are two walls, black on the top and black on the bottom, and then there's like a Harvard shield in between. And my goal is to think of this as a very simple maze with a very obvious entrance and exit, but just to start things off. I want to be able to move the Harvard shield up, down, left, and right, but as soon as it bumps up against and is touching a black line, I don't want it to go any farther. I want these things to act as though they're walls. So how might we do this? Well, notice here, let's see. I could do this from scratch, but it's going to take too long, I think. So I think what we would do is hide these down here and use this as an example of abstraction. Notice that this is all this program does. It first goes to a random It first goes to location 0, 0 in the middle of the screen, and then forever listens for the keyboard and feels for the walls. So what are these here? These pink puzzle pieces are abstractions. I implemented separately a bunch of lines of code that are constantly listening for up, down, left, or right so that we can move the actual shield. And every time we do that, we also feel for the walls so that every time we move up, down, left, or right, we make sure that we're not touching one or the other. Well, if I scroll down further, we can see what these abstractions are, the so-called implementation details. And again, I didn't just bang these out all at once. And indeed, I didn't bang them out at all. Carter did these for us. But indeed, these puzzle pieces do just that. It asks on the left here, how do you listen for a keyboard? Well, you ask the question, if the up arrow is pressed, then change the location, change Y by 1, move it up. If key down arrow is pressed, then change location Y by -1, move it down. If right arrow is pressed, change X by 1. If left arrow is pressed, change X by -1, thereby handling up, down, left, and right all of my movement. Meanwhile here, and in retrospect I would have slid it down more, meanwhile I'm feeling for walls as follows. If I'm touching the top wall, which itself is a black sprite, then change Y by -1. Go a little bit down below it. If touching bottom wall, change Y by 1, going a little bit above it, thereby preventing me from ever actually crossing it. And now you could imagine that this is a decent number of puzzle pieces, barely fits on the screen. And if we added those into the mix, you could imagine that my main program at the top of the screen would have been crazy long, like lots and lots of puzzle pieces and very hard to wrap your mind around what's actually happening. But with these abstractions, these new functions I created, can you still say what your program is doing without getting lost in the weeds of the details? And that, again, is abstraction. Now, once we have that capability, what if we add just one more, not just feeling for the walls, but bouncing something else? And let's introduce one other shield here. Suppose that we want to have an opponent in some game trying to keep that Harvard shield from getting from the entrance to exit. What if this sprite is designed to do a bit of bouncing and sensing, much like we did earlier? What if I have this thing going up and down constantly, checking for those same walls, but automatically moving up and down, not even letting the user control this particular sprite? I feel like with these two ingredients now, we allow the human to navigate their way through this world. We have the ability for the computer or CPU to be the opponent. I bet we could combine these into one final amazing project by, indeed, one of your own predecessors, a former student themselves. And I'm finding that this isn't here either. Damn it, stand by. This we should end on. All right, we're rewinding in time to last year because we're going to the source code studio. Carter, if you don't mind making a written note for me to fix this later. It's not, oh, did we not do that? Oh, we didn't do this last year because we had no audience last year. So we're going to go back in time an extra year. Stand by. Sorry for the anticlimactic ending. Source code. Where is it? Here we go. Whew, embarrassing. Let's go ahead and pull this all together using code that one of our former students wrote. I give you Ivy's hardest game. And at this point, we would probably have a volunteer or myself or Carter play the following game. Pressing space to start. And you'll see here, the maze is a little more complex than the one I made. But indeed, I can't move past those black edges. And it looks like I need to go to the sprite over here, getting the crest all the way over, and voila. OK, Yale's now in the mix. That sprite is moving left, right instead of my up, down. Same idea, though. I'm using my arrow keys to go up and then an angle, and voila. Now there's 2 Yale. So another sprite that appeared, presumably once my score was 2. And I think here, yep, we can have me yelling over the music. That's OK. Now MIT is coming after we have 3 here. But let me see if I can make past this. This, of course, gets very suspenseful if we have someone other than myself doing this. MIT, sorry, seems a little smarter in that it seems to be following me by pointing at this. So at this point, hopefully, some tension, some hilarity would ensue as the student playing this game makes their way to the final ending. And then we would close with some inspiring remarks, whereby at this point in the story, we would set the stage for your very first programming assignment. If you've never programmed before and are indeed among the 2/3 of students who've never taken CS, your job will be ultimately to make your very own program in Scratch, be it in animation, in interaction, or art, using these building blocks ultimately to do something that's correct, but using these ideas like abstraction to do something well designed too. With that said, we will see you next week. This then is CS50. Okay. Can we do just a couple questions with the audience before we depart? Let me put this on the screen. All right. Come on. Yep, that's okay. All right. Thank you all so much. I'm looking at the screen with all of our Zoom friends here. So many of you have stayed with us so long. Thank you for bearing with all my mistakes on the stage. Hopefully, this will come out all the better tomorrow, and we really appreciate it. Happy to take one or two questions, though, before we wrap up here. Let me see who's automatically on the screen here. See who might want to say anything here. Let's see. Whose faces and names are we seeing? Some new ones here. OK, Gabriella. Oh, we lost. Is Gabriella still there? Did you want to say hello? Gabriella. Yes, hi. I think we can unmute you.
OK, can you hear me now?
We can, yes.
OK, I think I just want to thank you, actually, because, well, I'm taking CS50X, so I've been learning a lot, and it really changed the way I see things, and maybe prepared me for some new challenges ahead. I'm 32, so I thought there weren't going to be new things ahead. So I'm really happy to know how much I can accomplish.
I'm really glad to hear
Thank
that.
you.
Well, welcome aboard. And I certainly hope there's a lot ahead, because I'm even more ahead than you, and I'm hoping some more remains. Should we go to the big screen one more time, Rungshin, here? One more time. I see we have some. Oh, well, let's see. They keep moving. Can you go back to the first screen? Back to the first screen. Let's see. A lot of movement on the screen. Yes, OK. Seeing a lot of waving here. Why don't we go ahead, and if you'd like to do one final wave, Rungshin, do you have the ability to do a screenshot on this computer? No? OK. Then we won't do it this time. Well, let's officially wrap here. Thank you all so much for joining us today. You're welcome to join us again tomorrow via Zoom if you can. It will also be streamed on YouTube. Hopefully, it'll be all the better thanks to your participation. We will see you on the internet. Thank you, and to the team here as well.